Well, good morning. This is Thursday morning, this 13th of July, 2017, 8:04 in the morning. Sorry, I'm a little late getting started. I thought I'd run down the hall one more time before we did start. So if we are going to go long today, that might be beneficial. But right now, I'm the only one in the classroom. It's supposed to be Math 238 differential equations. And like I said, I'm the only one here. So hope to see some people coming in. If they do come in and someone can stay, then we're planning to do an extra hour today, or 55 minutes, to cover the second part of my doctor's visit on Tuesday, when we're not supposed to have class. But if no one shows up today, then I don't think I'm going to go for 3 hours. I'll just go for the regular 2 and wait until someone can be here for that third hour. I feel like I'm required to do the hours when I'm scheduled to teach, but I'm not going to go talk to an empty room when I'm not scheduled to teach, unless that's the only option I have. So hopefully there will be other options. So I can't think of any other announcements that I need to make. I do know that coming up, I don't think it's next week, I think it's the following week, we have what they call planning hearings on the Birmingham campus, and I'm almost certain it's a Tuesday or a Thursday, and I'm thinking it's in the morning, maybe at 9 o'clock or something. So in that case, we may have to miss another class, because if it is 9, there's no point in coming out here and trying to teach for 30 minutes and then driving over there. I'll probably go straight to the Birmingham campus. So, but I'll find out and let you know next week. Okay, we were in Chapter 2, that's first order differential equations, 2.6, a numerical method, and we were looking at Euler's method. Now, Euler's method isn't fast, but it's doable, okay? One sort of neat thing about it is it's, I'm trying to think of the right word, programmable. So you can program on a computer to do it, and you don't have to sit and do it like we've been doing. But I did want to give you a flavor for what's Euler's method is. Now, last time we did example 1 on page 78, the first part where we attained an approximation of y of 2.5, y at x equal 2.5, using h equal 0.1, and now we're going to do 0.05. Now, advantage of 0.05, you're going to get better precision. Disadvantage of 0.05, it takes twice as many steps to get to 2.5. So if you go back to what we've doing, it would be, let me get my pen set up for the right color. Okay, it was a differential equation. Y prime is equal to 0.1 times the square root of y plus 0.4 times x squared. Okay, and like we said, and this is an initial value problem where y of 2 we know is equal to 4. Okay, quite often you will know some initial value. Otherwise, it's sort of hard to do Euler's method. So what we're going to do is find an approximation for y of 2.5. We know what it is at y at 2. Y of 2.5 using an h of 0.05. Okay? Now, let's plug in 2. So y of 2 is equal to, we know that's equal to 4, sorry, so not even go there. So we're going to next go to, okay, sorry. Okay. Euler's method, let me write that down next, okay? it says that yn plus 1, that's the second value, is going to be y at n plus h times your function, which is, this is your f of x y, okay? And that would be 0.1 square root of y n, okay, plus 0.4 times x sub n, okay, I'm going to write the x sub n squared. Okay, now our first step is y at, I'm going to put it this way, 2.05 is going to be y at 2, which is 4, plus your h, which is 0.05, times 0.1, okay, times the square root of y sub n. Y sub n is 4, so that's going to be times 2. Square root of 4 is 2, plus 0.4 times x sub n. Well, x sub n was 2, and 2 squared is 4. Okay? Now, I think I can do this one pretty much in my head. 4 plus 0.05 times 0.2 plus 1.6, just like we did before. I wish we'd have had that still. And except you're multiplying by 0.05, so this is 4 plus 0.05 times 1.8, okay, and 0.05 times 1.8, that would be 4 point, okay, 5 times 8 is 40, lose that 0, 5 times 1 is 5, plus 4 is 9, so I think it's a 0.09, yeah, 4.09, so that's your y of 2.5. So now we do, and if you look in the book, you'll see your y sub n was 4, y of 2.05 was 4.09, which we got. So your y at 2.1 is equal to your yn, your previous yn, that's now your 4.09, plus 0.05 times 0.1 times the square root of 4.09, okay, plus 0.4 times 4.09, okay. Now, that one I think may almost be doable, 4.09 plus 0.05 times 0.1, and I'm pretty sure, I'm trying to think, the square root of 4.09 I think is 2.3. Let me see, 2.3 times 2.3 is 9, no, it's not. Knew that shouldn't be the case. Oh, let me just do it. 9, 6, 6, 4, no, nowhere close. I would then say 2.03, but I don't think that will work either. But let's try it. Don't think that will work, but let's try it. 2.03. Be 906, no. 6, 4. Still wrong. Okay. So, I can't do this one in my head, okay, or even on paper easily. So, I'll just write down what it is. Well, we'll just leave it like it was before. Okay, you do the calculations. You got calculators. I didn't bring one in with me. Got calculators, plug it in, do the math, and the book tells us this comes up to be 4.1842. 4.1842. Okay? Now, if you look above, your first step before gave you, when x was 2.10, our estimate was 4.18. This is 4.1842. So it looks like by doing this, you're getting a little bit larger number, and that must be the direction we're heading. So then we do y of 2.15, and that will be 4.1842, and I'm pretty sure they've rounded that, plus 0.05 times 0.1 times the square root of 4.1842, and I'm certain I can't do that square root in my head, plus 0.4 times 4.1842. And if I had a calculator, I'd plug it in and hopefully get the same thing they did, 4.2826. Okay. And then you continue, a step at a time. Now, let's think what's happening here. Every time your new y is going to be your previous y plus that little bit of change, the 0.05, times your function evaluated at the previous value. Oh, wait. Sorry about this. I have botched that up. Not working well at all, and there's a reason for that. Right here, this is x squared, and I have not been putting my x squareds in there. Okay, so let me do that. Sorry, these wouldn't have come out right. I did that one in my head because your x was 2 squared is 4. Okay, this time the x is 2.1 squared. Okay, and this one would be, I'm sorry, 2.05 squared is the previous x. .05 squared, and this would be 2.1 squared. Okay, sorry about that. That should give you the correct answer. The y goes in the square root, and the x, previous x, is what you're squaring. You proceed like that, and so what I was saying, you take the old y value and then add the incremental increase to what your function was at the previous value for x, and that gives you your next approximation of what your y is. And the next one would have been, I'm not going to write it all down, 2.2, and that would, if you follow in the book, 2.2 is 4.3854, and if you look at the other previous 4.2, is 4.3768. So again, a little bit more refined value. Obviously, your first value was undershooting it a little bit. This one may be overshooting it just a tad, but it should be quite a bit better. And you proceed and keep going until you get y of 2.5, which is what you're looking for, and from the table in the book, you see they get that to be 5.0 0.997. When we did increments of 0.1, you got 5.0768. So to 2 decimal places, you're still good. If you needed 3 or more places, then you probably need to keep going and doing smaller and smaller increments. But again, all this is programmable, and you can get your calculators to do this fairly rapidly. It's a lot of operations, so it does take some CPU time, so you might have to sit there and take a sip or two of coffee or something in between, but you will get, ultimately, a pretty good answer, okay? Now, how good do you get? How good do you want to get? Do you want to get to the nearest 3 digits? Then you keep going until you don't get a change in that 3rd digit. Like right now we had within 2 digits. So a lot of times you want at least 3 significant digits. Sometimes you may want more precision than that. There's usually a test you can do, and the computer can do this as well. Look at the current answer, see what the previous, pull back up the previous answer, and see if it differs by more than 10 to the minus 3, 10 to the minus 4, 10 to the minus 2, whatever error precision. And if you don't get any better than that, then you say that's going to be close enough, okay? And so that's typically where we go. So, without doing any more of those, especially since I don't have a calculator, let's move on to example 2. All right. Consider the initial value problem, y prime is equal to 0.2xy. Now, if I am not mistaken, this, I think, is one we had way back, okay? And we have a y of 1, initial value problem, so we have some initial value when x equal 1. We got y equal 1, okay? It says use Euler's method to obtain an approximation of y of 1.5. First using h equal 0.1, and then h equals 0.5. 0.5, okay? Now, last time we did the same thing. However, last time we had a differential equation that, frankly, I saw no way whatsoever of solving analytically. So we were having to use a numerical approximation. This time, we've already done this one, I think. Maybe not all the way, yeah, and it's not a hard one to do analytically, and we can get exactly what our answer is at 1.5, but they're wanting us to try it using Euler's method. So I'm not going to do all the math, but I'll show you the first steps, okay? And here's Euler's method. Y of n plus 1 is equal to y of n plus 0.1, that's your h, times 0.2 x sub n, y sub n. Okay? So your y of n plus 1, the first one is going to be y at 1.1, because you know y of 1 is 1, plus 0.1, that's your h, times 0.2 times 1 times 1. Not too hard, okay? This will be 1 plus 0.1 times 0.2, okay? 0.2, which would be 1.02. See that? 0.1 times 0.2 is 0.02, and 1 plus that is 1.02. So, that's what you got for y sub 1, or y of 1.1, okay? And these are approximate. I probably should be putting approximates there. They're just putting in a table. You know it's not exact, but it is, okay? Let's try the next one. Y of 1.2 is equal to 1.02 plus 0.1, your h, times 0.2, that's part of the problem, times your x, which is now 1.1, the previous x, 1.1, times your previous y, which is 1.02. Now that's not hard math, but it's not something I can do in my head. So let you do the calculation there, and I'll use what they got in the book as 1.0424. Okay? Y of 1.3 with one more thing is 1.0424 plus 0.1 times your 0.2. 0.1 is your h, 0.2 is part of the problem, times your previous x, which is 1.2, times your previous y, which is 1.0424. Okay? And pull out your calculator. Not a hard thing to do on the calculator. I can't do it in my head easily. And this gives you 1.0675. Okay? Now notice each increment seems to be going up by about 0.02, a little bit more than 0.02. And that almost comes from this right here. Okay? So y of 1.4 would then be your y of 1.3, which is 1.0675, plus your h.1 times your 0.2, which is part of the problem, times your previous x, which is 1.3, times your previous y, which is 1.0675. Okay? Do that, and you get y of 1.4 to be 1.0952. 1.0952. Like I said, a little bit more than 0.02, so that one went up a little bit more. And then finally, your last one, y of 1.5, will be your y of 1.4, which is 1.0952, plus your 0.1, which is your increment, times your 0.2, which is part of the problem, times your previous x, which is 1.4, times your previous y, which was 1.0952. And when they do that, they get the first approximated answer, 1.1259. Okay. Now, next thing we're going to do is do it with 0.05. I wish I had room to do it. I don't. But what I think I'll do is erase this. I'll keep that. And I'll see how much I can keep. Yeah, I wish well, I'll just go back and do it. Okay. The rest of it's history. Okay. Oh, I shouldn't have erased that. Okay. I could have done better, but all right, I'm going to leave the previous one there. And we'll start with 0.05. Or h, our increment of 0.05. Okay, so 1.05 will then be 1, which is your previous h, previous y, 0.05 times 0.2 times your previous x was 1, your previous y was 1, and that's 1 plus 0.05 times 0.2, just like we had before, and this would be 1.01, if I'm not mistaken. 0.05 times 0.2 would be 0.010, which is 1.01. And that's what they got. Good for them. So the next increment, 1.1, was 1.01 plus 0.05 times 0.2 times the x value. Previous one was 1.05 and the previous y was 1.01, and I can't do that in my head, so I'll read it from the text, and that's 1.1, 1.0206, 1.0206. So it looks like now they're beginning to go up by about 0.01 each, but you know it's a little more than that, so it will always be a little more. 1.15 will be the next one. That would be 1.0206 plus 0.05 times 0.2. I should have left all those in there. Times your previous x was 1.1. Your previous y 1.0206. Okay? And that came out to be 1.15. The book has 1.0318. 1.0318. Okay? 1.2 was 1.0318 plus your 0.05, that's your increment, times 0.2, that's part of the problem, times your previous x, which is 1.15, times the previous y, which is 1.0318, and they get that to be 1.0437. 1.0437. So again, a little bit more than 0.01 each time. But let's go back and just compare. The 1.1 we got this time was 1.0206 before we got 1.202. So a little bit larger. 1.2 this time got 1.0437. Last time got 1.0425. So again, you're getting a little greater value. So it's basically an increasing function. You're getting a little bit better approximation. Now, don't have room or time to do them all, but let's do the last one, and that's 1.5, which would be the y at 1.45, which would be 1.1133, 1.1133 plus 0.05 times 0.2, and your previous x was 1.405, no, 1.45, sorry, where did the 0 come from? 1.45. The previous x was 1.45. The previous y was 1.1133. And when you do it with the 05, that came out 1.1295. Notice here, it looks like we could be within 3 significant digits. The first one would have rounded to 1.13. This one rounds to 1.13. The question is, does it stay that low or does it keep creeping up? Well, let's just integrate it and see. This problem was dy dx, that's your y prime, is equal to 0.2 xy. Okay? Well, I'm going to write that in differential form, which would be dy is equal to 0.2 xy dx. And now I'm going to divide both sides by y. Okay, that'll wipe out the y's here, and that gives you the log of y is equal to 0.2 x squared, right, over 2, so that would be 0.1 x squared, okay, plus some c. But before we do that, let's go on and take an e of both sides. That will give us a y is equal to e to the 0.1 x squared. And actually, if we had done that as being a log c, then that would have been times this. So basically, our constant comes out being in front. You can go back and check, and that's what it actually turned out being. I'm pretty sure. Now we use our initial condition, and we have 1 is equal to c e to the 0.1 times 1, because 1 squared is 1. So we now have c is equal to 1 over e to the 0.1, which just is some value, okay? Now, wish I had a calculator. Your answer then would be y is equal to 1 over e to the 0.1 e to the 0.1 x squared. And if we plugged in, really regret not having it. In fact, I think I'm going to run down to the office and pick up a calculator just to see. Well, I'll just use the book. There's no reason not to. The actual value they tell us is 1.1331. Okay? I don't have a calculator in here to check, but I'll take their word for it. So they get y at 1.5 to be, when you plug in 1.5 squared and do e to, yeah, all that kind of stuff. They claim it's 1.1331. Okay? Now, we said we rounded to 1.13, and their actual value is 1.13. Now, we were a little bit off, but not so awfully bad. What they do is the absolute error, and for the first one, they were off by minus, and let's see if I can do the subtraction, 1.1331 minus 1.21259. I can't write. Okay, let's see if I can get that in there a little bit better. Okay. And when you do that subtraction, it's 0.0, let's start from here. That would be a 2, 5 and 12 is 7, 1.007. And they actually rounded up to 3. They must have kept some numbers in there. Well, that was your absolute error on this, and that, by the way, is a negative. I don't know why they don't. Oh, absolute meaning without sign. So that's why they said that. The absolute error is 0.0073, they claim. And if you take that error and divide it by your actual value, 1.1331, that gives you your relative error, and that's 0.64, okay? And by the way, that's a percent too. It's, so you multiply by 100. So it's a 0.6%. Not bad, less than 1% error. Okay? On your 0.05 approximation, that's your 1.1331, subtract 1.1295. We did 59 last time. We subtract this, you get 0.00, let's do it from this side now, 63, yeah. So your absolute error is 0.0036, better, in fact, half that of 0.0072, and when you do your percent, 0.0036 divided by 1.1331, you get a percent, which is, I'm guessing about half of that, 0.32, yeah, 0.32. And that's a percent, by the way, okay? Very small, so you're within 0.0, basically 4, okay? Percent error 0.003. Now, sometimes they want your precision to be as much as 0.001. If that's the case, fairly good, certain that just having this again, doing 1.01 as your increment would get you awfully close there, and 0.0005 would probably certainly get you there. Okay. Now, again, relatively easy to do, tedious, but fairly easy to program and get a computer to do it for you. And you can always have the computer go back and check how precise you are and see if you want to keep going. Okay, you set the precision that you want to do. Now here's a little caveat. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Though attractive for its simplicity, Euler's method is seldom used in serious calculations while we've been wasting our time on it, okay? But to give you an idea. It was introduced here simply to give you a first taste of numerical methods. We'll go into greater detail in discussing numerical methods that give significantly greater accuracy, notably the fourth order Runge cutter method, cut-up method, referred to as RK4 method. That's in Chapter 9 at our pace, and there's a little term we have left, not going to get there. But if you do need to know it, go over there, okay? Now, there are also things they call numerical solvers, okay? And they say many of these are commercially available, either embedded in a larger software package such as computer algebra system or provided as standalone packages. Some software packages simply plot the generated numerical approximation. Others generate hard numerical data like in our tables there. I'm guessing that was done by something like computer algebra system, and getting answers that way. And you get these numerical solution curves. Now, hopefully you have books. If you turn to page 80, the one we were just working on, okay? Yeah, I think that's the one. It shows the exact solution in the blue curve, nice smooth blue curve. Euler's method, and I think 0.1, you see is the yellow. It was deviating fairly widely, pretty good for the first one or two values, but then after that. But then the RK4 is guaranteed to work at certain points. That's what it does. It actually pings on the actual points, but does looks like a linear approximation in between. Okay. Now, they have a blurb here on using a numerical solver. I think if you do use one, you'll probably get plenty of opportunity to look at it. But you'll see sometimes they do. The figure they show here, not very helpful numerical solution curve. This looks like it's obviously a discontinuous function, and you would think those would really have problems with it. And indeed it does. So they're not a great answer for every problem, but they can help speed things along. Okay, that finishes 2.6. Now what I was going to say, back when I was taking graduate courses and did some, these were either math or computer science courses, we did what they call either finite difference models or finite, what was the other name for it? They're awfully close sounding in names with a little bit of a subtle difference between the two. Finite difference problems or finite, I can't remember the other name for it. But basically those used your differential equation. If you had written it the way we did there, we would just do well, it's a lot like Euler's method, okay? The finite difference or finite whatever the other one is. And again, easy to do on the computer. But Runge-Kutta probably is easily programmable as well, but yeah, not quite going to get you there either. All right, let's look at exercise 2.6. Do number 1, do number 3, and then do any of the odds 5 through 9. Do number 11, and that's all you have to do. Now, some of those may get very tedious, but hopefully you can speed it along once you get basically you get your algorithm down. Now there's a chapter 2 in review here. We are finished with chapter 2. And again, any of the odd number exercises, I think those answers are in the back, 1 through 11. Really worth your shot to take a look at those. Number 13, we did some like that in class. Number 15, or any of the odds, 15 through, 15 or 17, I'll say. Then any of the odds, 19 through 25, either 27 or 29, or both if you choose, 31, 33, any of the odds, 35 through 39. Okay? Some of those may get a little more difficult or esoteric or something, but I'll let you do. Just don't wear yourself out, but those would be additional problems to help. Now, I had planned to give you your second test today. I have gotten the first test back for both of you. I have one graded, the other one got so close to getting it graded, but had some things come up that I couldn't quite get time to do. So chapter 3 is on modeling with first order differential equations. Great chapter, but if I remember right, I don't think there was much about modeling in the course description. So I think what we need to do is go on to chapter 4. And chapter 4 is higher order differential equations. Okay? So we've done first order, now let's look at some higher order. Now, they start with preliminary theory. Okay, let me see, we've gone about an hour now, not quite an hour. It is a fairly decent breakdown. I usually don't take one this soon. I do need to go clear my head, so let's take a quick break. Okay, we're back, and we've got a student. That's great. Okay. Chapter 4, we skipped 3. 3 was on modeling with first order differential equation, which is a great chapter, but I don't remember there's that much modeling in the course description. I don't believe there was any, but if there was, it wasn't much. But chapter 4, higher order differential equations, definitely was mentioned by name. So let's hit that. We now turn to the solution of ordinary differential equations of order 2 or higher. Okay? In the first 7 sections of this chapter, we examine the underlying theory and solution methods of certain kinds of linear differential equations. The chapter concludes with a brief examination of solution methods for nonlinear. Guess what? We're going to stay in the linear part. We're not going to have time to get through section, what was it, 8 or something like that. So we're going to stick with linear. In first order, we did nonlinear as well, but in second order, we're just going to stick with the linear. Okay. So here's a little bit of a review nomenclature. Recall that a general solution is a family of solutions defined on some interval I that contains all the solutions of the differential equation that are defined on I, on that interval I. Only in the case of linear first-order differential equations were we able to obtain general solutions by paying close attention to certain continuity conditions imposed by the coefficients. Because our primary goal in this chapter is to find general solutions of linear higher-order differential equations, we first need to examine some basic theory of linear equations. So that's what we're going to hit now, preliminary theory. That's 4.1. Okay, here's what we got. A typical initial value problem looks something like this. And back in section 1.2, we defined some initial value problems for general nth order differential equations. Okay, so this is sort of a repeat of that, maybe carried a little bit beyond. For a linear differential equation of nth order initial value problem, IVP, this would be typical. Solve a sub n of x, okay, dny dx to the nth, plus a sub n minus 1 of x, dn minus 1 of y, dx to the n minus 1, plus a sub n minus 2 of x, dn minus 2 of y, dx to the n minus 2. Get the general idea? Plus dot 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 until you get down to a sub 1 of x, dy dx, plus a sub 0 of x, y. And that's equal to some g of x. Oh my goodness. Okay. What does this mean? Okay. What your a's are coefficient functions. Coefficient functions. Now notice, for this to be linear, okay, for this to be a linear equation, that's all we're going to deal with in this chapter as far as we get in, it will be linear. Notice that your derivatives are always to the first power. They're the nth derivative, but they're to the first power. It's not dy dx times d2y dx squared. That would not be linear, okay? Or dy dx squared, or to the fourth power, to the 3/2 power, or to 0.5 power. You couldn't. That would not be linear. So all your derivatives are only to the first power with no crosses in them. All your coefficients of those derivatives are functions of x and x alone. You can't have any y's in here, okay? Otherwise, it's nonlinear. The only place you have a y is this, which is the zeroth derivative, meaning the function itself. This is the first derivative, this is the zeroth derivative, which is the function itself. And that's just a y. It can't have y squared or anything else. And then that's equal to some function of x alone here too. So all your coefficients are functions of x alone, and your what's equal to on the other side is a function of x alone. And then all your y's show up as derivatives of y or the function y itself, all to the first power, none to the fractional powers, none to the higher powers, no crosses. You can't have dy dx times a y. You can't have anything but a single term of either the derivative of y or y itself. Okay, so that's your general form. Subject to y of x0 is equal to y0. That's your initial condition. But you don't just have one, you'll need another one, y prime at, and they usually use the same value, x sub 0 would equal to some other value y1, not necessarily y0. Definitely not necessarily y0. Y double prime of x, of x0 would be some other value, that's a 1 there and a comma, left off one of them, I couldn't tell which, equal to some y2, comma, dot, 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 until you get up to y to the n minus 1. Now that's the n minus first derivative of y evaluated at x0, okay, and that would give you some y of the n minus 1. Okay, now just see. This was a y0, first derivative was a y1, second derivative y2, n minus first derivative y to the n minus 1. Okay, now actually that gives you n initial condition equations. Okay, it's just that you're starting with 0, 1, 2, 3 rather than 1, 2, 3, 4, 5 up to n. 0 to 3n minus 1 is still n equations. Okay, since you have an nth differential equation, you need n initial conditions. Okay, and like I said, we usually evaluate all those derivatives at the same x0 value. The thing is, they're going to give you different values. Now, I kind of don't care for using y. This makes sense, y0 here. I kind of wish they'd have just used something else. B0, B1, B2, something like that, just to let you know it's some number, because using a y, it makes you think it has to do with your function y. It really doesn't. This one kind of does, but it's actually a y value. The next is actually a value of your first derivative, not a value of a function. Okay, so that's why I almost wish they'd have had some other letter there just saying it's a constant like b. You don't usually use c because that's usually your integration constant, so that's why I just picked something else like b. But it's okay. There's nothing wrong with that. It's just I wish they'd have used something else. Now, there is a little statement here about existence and uniqueness. Back in section 1.2, we stated a theorem that gave conditions under which the existence and uniqueness of a solution of a first-order initial value problem were guaranteed, and the theorem that follows gives sufficient conditions for the existence of a unique solution for that type of a problem. Okay? Now, you have your text. Okay, good. All right. So I'm going to read it rather than write it. Let a sub n of x, a sub n minus 1. These are your coefficient functions here. Okay? A sub n of minus 1 of x, a sub n minus 2 of x, dot, 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 down to a sub 2 of x, a sub 0 of x, a sub 1 of x, a sub 0 of x, and also your g of x, which is on the other side by itself. Be continuous on the interval in question. Okay? They have to be continuous there. You cannot solve a differential equation if one of your functions takes off and goes to infinity. Yeah, no way you can do that. One of your coefficient functions, the g function, you can't. You have to have well-behaved functions on the interval. Every one of those functions of x have to be well-behaved on that interval of x. Okay? Now, the other little caveat here, this sounds a lot like quadratic. Your a sub n of x can't be 0. The reason for that, if a sub n of x was 0, this term isn't there anymore. Well, now you don't have a nth order differential equation. You have an n minus 1 order differential equation. And if we're talking about an nth order differential equation, you got to have the nth thing. But if your a sub n was 0, you wouldn't have it. It would wipe it out. So that one can't be. The other a sub n's, any of them, all of them could be 0. You know, wouldn't be a very interesting problem, but they could be. Okay. For every x in the interval, let a sub n of x not be equal to 0 for every x in the interval. Again, you've got the interval there. You can't have the a sub n of x be 0 anywhere for any value of x in the interval. Okay. If x equal x0 is a point in the interval, then the solution y of x of the initial value problem with all those initial value features to it exists on the interval and is unique. So what's the requirement? That your a sub n of x can't be 0, all your a of x's and your g of x be continuous on the interval. Thought there was somewhere there they said it had to be, yeah, continuous. That means you don't have any breaks or taking off and going to infinity or anything. And x equal x0 is a point in the interval. Then the solution exists and is unique. So let's look at example 1. Okay. Three y triple prime plus 5y double prime minus y prime plus 7y is equal to 0. Okay? And we need some initial conditions. Y of 1 is equal to 0. Y prime of 1 is equal to 0. And y double prime of 1 is equal to 0. Okay. Now, number 1, right off the top, we can find one solution. Guaranteed. Y is equal to 0. Because if y is equal to 0, 7y is equal to 0. The first derivative of 0 is 0. The second derivative of 0 is 0. The third derivative of 0 is 0. And they all add to be 0. Okay? So that's a trivial solution. And in that sense, now this is a different phraseology from what we used in the previous chapter. This is a homogeneous equation because that's equal to 0. And by the way, y prime of y of 1 is equal to 0, y of 1, yeah, all those equal. So y equals 0 obviously is going to be a solution. That's called the trivial solution because you really didn't have to work very hard to get it. I mean, that's for what they call a homogeneous equation which equals to 0, that's always going to be a possibility. Okay? Especially since all your initial values are 0 as well. Okay. It's a third order equation. The coefficients are all linear, okay? In fact, they're all constants, okay? So therefore, there's no problem with those being continuous, okay? Everywhere, for all values of x, they're constant. So yeah, this has a unique solution. Hence, since it is a unique solution, and we know that y equals 0 is a solution, that has to be the only solution. The only solution. So all that writing for just a thing on the interval containing x equal 1, because that's where you are. Now, if you're on some other interval somewhere, you may have some more work to do. So that was almost a trivial example. Okay, let's do example 2. All right, let's keep from confusing them. We'll go and clear that, even though it's not taking much room. All right, here's a function, an equation. Yeah, sort of don't like it, but I guess we need to do this. They first give us a function. Y is equal to 3x squared, 3e to the 2x, I can't talk, plus e to the minus 2x minus 3x. It says verify that that equation, that function, is a solution for the initial value problem, y double prime minus 4y is equal to 12x. Given the initial condition y of 0 equal 4. Now how many more initial value things do we need? Okay, one more they do give us, and that's y prime of 0, y prime, yeah, of 0 is equal to 1. Okay, now, a first order needed 1, a second order needs 2. So basically the order of the equation, linear, that you're going to need that many. Okay, so absolutely right. Now, all they're asking us to do is verify that solution is a solution for this and that. Okay, so Les, where would you begin? Where would you begin? There's a couple places you could do first. What do you want to do first? Take a derivative. Sounds like a good answer for most calculus classes and differential equations. Take a derivative. That's, yeah. What's that? Right. Okay, and what would be your first derivative of that equation? Okay, you said 6 e to the 2x, absolutely. 3 times e to the 2x times the derivative of 2x, which is 2, so 3 times 2 is 6, okay? Minus 2 e to minus 2x minus 3. Very good. What next? Take a second derivative. Take a derivative of that derivative. And what do you get? 2x done. Okay, so let's plug this and that. We don't really need that one, but we had to do it to get to the second derivative. So let's plug this in. That'd be 12e to the 2x minus, plus 4 e to the minus 2x, that was your y double prime, minus 4 times your y, which was, I'll write it out, 3e to the 2x, plus e to the minus 2x, minus 3x, and supposedly that's equal to 12x. Let's see if it is. Well, this is 12e to the 2x plus 4e to the minus 2x minus 12e to the 2x minus 4e to the minus 2x plus 12x. Is that equal to 12x? Well, here's a 12e to the minus e to the 2x minus 12e to the 2x. Those add to 0. Here's a 4e to the minus 2x minus 4e to the minus 2x. Those add to 0, and sure enough, 12x equals 12x. Except we still need to check our boundary conditions, our initial conditions. So let's do that. Let's plug in a 0 for the y, for the x here, and that would give you y of 0. Plug 0 in for x in this y. Yeah, that's what you're doing. See what you come up with. What's e to the 0? 1. So this will be 3 plus, second, 1 minus 0. You plug a 0 in there, nothing. What does that give you? 4. Ding! That one checks. The differential equation checked. The first initial value checked. Let's do the second one. Here we do need the y prime. Glad we did it. And evaluate this at 0. Y prime at 0 would be 6 minus 2 minus 3, which would be what's that? 1. And that checks too. So yes, your differential equation checked, your first initial condition checked, and your second initial condition checked. Yep, that satisfies it all. Okay? Yay, they told us something, said verify it, we did. How did they get that in the first place? They're not going to tell you for a while, but we'll get there. Okay, I'll try to move pretty quickly, but they want you to, what's that? No, it wasn't. Okay? All right. The requirement in example 4.1.1, the ace of I of x, when I is 0 through n, be continuous, and the ace n of x not be 0 for every x in the interval, are both important. Specifically, ace of n of x equals 0 for some interval x in the interval. Then the solution of the linear initial value problem may not be unique or even exist. Okay? And here's what they're going to ask us to do now. And I guess there is a method to this. I guess I just want to get on with it. Show me how to do it, you know. Not this, well, do this and see what you get. Do this and see what you get. Well, tell me how you got that, okay? But here's the next one. Here's a y is equal to c x squared plus x plus 3. Okay? They want you to verify that's a solution for the initial value problem x squared y double prime minus 2xy prime plus 2y is equal to 6, subject to y of 0 is equal to 3 and y prime of 0 is equal to 1. And they say on the interval minus infinity to infinity. Okay? Okay. And it says for any choice of the parameter c, which is a bit bizarre because you would think if you had a parameter and initial values, enough initial values, which we do, 2 of them, that you shouldn't need a parameter in there, okay? So let's do what they told us to, but I can tell you right now, we have a problem, Houston, okay? And the problem is the interval we're talking about, because in that interval, that's the interval of x, your a sub n is actually 0 at one value when x equals 0. So basically, I think what they, and then they're evaluating x equals 0. So I think we may have multiple problems here. But they said verify it. So let's verify it. What's the first thing we're going to do? Yeah, take a derivative. Y prime would equal 2cx plus 1. And y double prime would equal 2c. Okay? Or not 2c. Okay. Now, we verified that. Let's verify the second part. Oh, wait, no. We haven't plugged it in yet. Let's plug it in. So let's get x squared times 2c. So that'd be 2cx squared minus 2 times 2x times 2cx plus 1 plus 2 times cx squared plus x plus 3, and we're wondering if that's equal to 6. All right. For some reason I'm clogging up again. I don't know what. I got water, clear it out, but man. Okay. Let's clear our parentheses, see what we get. 2cx squared minus, that's a 2x there. Distribute the 2x across the parentheses. What do you get? 4cx squared, and then distribute this one, and you get a minus 2x, okay, plus 2cx squared plus 2x plus 6, okay? And that's supposed to equal 6. We don't know, but it is what it says, okay? Let's try it. Here we have a minus 4cx squared, a plus 2, and a plus 2cx squared. That adds the 4. This is minus 4. That goes to 0. So far, so good. Here we have a minus 2x plus 2x. And we got 6 equals 6. Yes, it meets the the differential equation is satisfied with that solution. Okay? Now we got to check our initial values. Okay? Certainly when x equals 0, y is equal to 3. Right? Okay? Y prime, when x equals 0, y prime is equal to 1. Yes, everything's looking really hunky-dory. Okay? The problem, though, is that at x equals 0, your first coefficient, x squared, is also equal to 0, and that was not allowed. Okay? Now, it's easy to forget that, skip over it, or something like that. But you can't. That is a problem. How does it show itself? Everything seemed to work well. How does it show that it's a problem? Okay? Well, basically, it's what bugged me at the beginning, is that you have a parameter that you have a an infinite number of solutions. Choose C equals 0, C equals 17, C equals negative 3 pi. You don't have a unique solution, you have a whole family of them, but the problem is that all stems from the fact you didn't meet your initial requirement that the x squared, the coefficient of your leading term, can never be 0 on the interval. Now, I guess there are I was going to say, if you chose an interval that didn't include 0, then you might say, well, that might work. But it won't work here because, remember, your value, your initial value, your x of 0, has to be in the interval, okay? So this says 0 has to be in it. This says you can't have 0 in it. So therefore, it's almost, it looks too good, but it can't be true. Well, the main thing is you got infinite number of solutions where you should have a unique solution. All right, now, let's look at now boundary value problems. And I'm pretty sure that you could easily run into these in ordinary differential equations, okay? I know that you run into these in partial differential equations pretty much big time, okay? But in ordinary differential equations, you still could. So let's take a look at what we mean by a boundary value problem. Another type of problem consists of solving a linear differential equation of order 2 or greater in which the dependent variable y or one of its derivatives is specified at a different point, okay, or they are specified at different points. Here would be, I may have to go get something to drink. I don't know what is wrong in my head. It did this yesterday. Of course, I talked for almost 9 hours yesterday, huh? Okay. You want to take a break now? Well, I mean, if you want to go a little bit longer, are you planning to stay extra today? Okay. I was trying to, I just broke 30 minutes ago. I think, surely I can make it. I hope I can. Okay. All right. Okay, so here's a boundary value problem. Looks a lot like this before. A sub 2 of x d2y dx squared. That's looking pretty close to what we had before. Plus a sub 1 of x dy dx plus a 0 of x y is equal to some g of x. Okay, most generic form that we could do. Now, here is the subject to. Y of A is equal to some y0, and y of B is equal to some y1. Now, in that situation, I really like the fact that they did use y's there, y0 and y1, because those are y values, because you're evaluating y at two different x's. So these are boundaries where the things have to meet, okay? It's called a boundary value problem, or a BVD. VVP rather than an initial value problem, which is the IVP. Okay? I was in a Christian organization, InterVarsity Christian Fellowship, and they had a press, a really great press arm that was InterVarsity Press, and that was IVP. So I'm used to IVP. Okay. Great books. If you ever see an IVP book, it's usually a pretty good book, published by IVP. Okay. The prescribed values, YV equal was, okay, those are the boundary conditions. These are called the boundary conditions. The others are called initial conditions if they're at the same point. Okay, a solution for the foregoing problem is a function satisfying the differential equation on some interval I containing A and B, whose graph passes through the 2 points AY0 and BY1, because that was the X value, Y value, X value, Y value. Okay? Now, for second order differential equations, other pairs of boundary value conditions could exist. You could have had the second one that y prime at A was equal to some, and again, this is where I don't like calling it a y0. I would call it something else. And yb is equal to y1. Or you could have had it y prime at A is equal to y0. Sorry. And y prime of B is equal to some y1. Okay? So you can mix or match just about any way you want to. You just need two conditions. The problem is that doesn't guarantee a unique solution. It should for an initial value problem if you have two conditions, but in a boundary value problem, it may not. Okay? And note that the y0 and y1 are arbitrary constants, so therefore I would have named them something other than y, but it's okay. These three pairs of conditions are just special cases of the general value boundary value problem, which you could write as this, that some alpha 1 y of A plus beta 1 y prime at A is equal to gamma 1. They really are liking their Greek letters, aren't they? Alpha 2 y of B plus, okay, beta 2 y prime of C, y prime would be, yeah, is equal to gamma 2. I'm sorry. I'm going to have to go get something because it's to break a class twice. That was because right before class, or right as I was starting class, I got a case of hiccups. And I kept thinking they're going to go away, they're going to go away. And they didn't, so at break time, I went down and my mom had taught me if you drink water really slowly, that sometimes that'll do it. And it seemed to stop them. Came back and taught for about another half hour, 45 minutes, and they came back. I mean, just out of nowhere, it came back again. And I tried to slug through it again, and I couldn't. I said, so yesterday I did take a break twice. I said I don't think I'd taken a break twice. Well, I did yesterday, but that was a different issue. So, anyway, these possibilities here of your function evaluated at one value, another value, the derivative evaluated at one value, and function at another value, the derivative at one value, the other derivative at a different value, or the one we did to begin with, which was, they have left out one, haven't they? Y of A, Y prime at B. Okay, that's another possibility. So they didn't put that down here. Y of A, but Y prime at B. You got Y of A and Y of B, Y prime of A and Y of B, Y prime of A and Y prime of B. They left out Y of A and Y prime of B. So there were 4 sets. So those are all covered by this thing. Okay, this combines every possibility you can have, and so any values that you could have there, that can be your generic form. They're just special cases of the general boundary value conditions. That. Now, here's example 3. That's where we're going to go next. Okay. If you think back, if you had enough initial conditions, then you expect to get a unique solution. Okay? However, with boundary value problems, you can have a unique solution, or many solutions, or no solutions. Okay? So when you start picking different points that you're going to, you can open up some cans of worms. Okay? So if you go back to example 9 of 1.1, way back, we saw that the 2-parameter family of solutions of a differential equation, and here's what it was: x double prime plus 16x equals 0. Okay? Now, your independent variable here, they haven't explicitly said, but most of the time if you don't see it, you assume it's t, especially if you have x. If that was y double prime plus 16y, then you assume it might be x. It could be t. But if it's x, usually it's going to be a t, unless they designate otherwise. Okay? We found out before, back in example 9 of section 1.1, that x equal c1 cosine 4t plus c2 sine 4t is a solution to that. And we could go back and do all that. We certainly could if we know what to do. The first root of this would be 4 minus 4 c1 sine 4t, right? Plus 4 c2 cosine 4t, and your second derivative would be 16 minus 16 c1 cosine 4t minus 16 c2 sine 4t. And then if you, that's your second derivative, minus is there, plus 16 times this, yeah, everything goes to 0. So that's a 2-parameter solution that fits everything in there. Okay. Now, suppose that we now wish to determine the solution that further satisfies the boundary condition, x of 0 is equal to 0, and x of pi halves is equal to 0. So that's not an initial value problem, that's a boundary value problem. You got 2 solutions, 2 derivatives. That should be, you would think that it might be sufficient. Okay? Now, if you plug them in 0 for your t there, okay, you would get x at 0 would be c1 cosine of 0, right? Because sine of 0 is 0, so you lose the C2. Okay? When you do x of pi halves, you get cosine, okay, wait. You get C1 cosine 4 times pi halves would be 2 pi, okay, plus C2 sine of 4 times pi halves would again be, that would be sine of 2 pi. Well, sine of 2 pi is still 0. And cosine of 2 pi is 1, right? So you get, in both of these cases, and we find that x of 0 is 0, you get C1 equals 0. But you don't get any value for C2 because both of your initial conditions, boundary conditions, you lost it, okay? So you can't determine your values. You get C1 equals 0, and you don't identify what the second one is. So therefore, there you have infinitely many solutions. Any value for C1, C2 that you put in there is going to be a solution, okay? Because, and they show the graph, you see it there, not only is your initial condition 0, but then you have other places where it's 0. Every node there of that sine curve is going to be at 0, and that really doesn't give you very much, okay? So, you have infinitely many solutions. It's a one-parameter system. You have x equal C2 sine 4t. For any C2 you choose, you get a solution, okay? So you have infinitely many solutions. Now, what if your boundary value was changed to this? X of 0 equals 0, and x of pi eighths is equal to 0. So now your second boundary condition is equal to 0. Okay? So let's plug it in. Your same solution should be doing. So you have x of pi of 0. Oh, that gives you the same thing as before. Your C1 is 0, C2 could be anything, okay? So we already have that. So let's do the x of pi eighths and set that, it's supposed to be 0. So that's going to be C1 cosine of 4 times pi eighths would be pi halves, okay? Plus C2 well, actually, your first one, if you remember, that gave you C1 was equal to 0, right? So your first condition gave you that, so you don't need that. So now we're down to just the second one, which is C2 sine of pi halves, okay? Because 4 times pi eighths is pi halves. Sine of pi halves is 1, so you have C2 is also equal to 0, okay? Guess what? That's just a trivial solution. Your solution, basically, you get no solution. It's C1 is equal to 0, C2 is equal to 0, so x equals 0. Well, x equals 0 is your trivial solution, okay? And that is your one and only solution. And so x equals 0 is the solution for the new boundary value problem. It can be shown as the only solution, the only one that'll work. So let's try something different, okay? This time we're going to do your x of 0 equals 0, just like we did before. But this time we're going to, the second condition is x of pi halves is equal to 1. Okay, so let's go in and it's just what we had to begin with, except that this is equal to 1, not 0. Okay. Okay. Equal to 1. All right. So let's plug again. If you plug in x equals 0, just like before, you come up with C1 equals 0. Okay? I don't know what that other mark is there. Let me get rid of it. Okay. So C1 is equal to 0. Let's plug in the second boundary value condition, and that would be x equal, you've already determined C1 equals 0, no reason to write it down again. C2 times the sine of 4 times pi halves would be 2 pi, and that's equal to 1. That's ridiculous, okay? Because sine of pi of 2 pi is always, okay, sine of 2 pi is always 0. So this can't possibly be true because 0 can't equal 1. And if that's the case, this has no solution. If you get a situation that can never be true, okay, that 0 is equal to 1, doesn't happen in this universe, so you say that's a no solution. So we saw in the first case, infinite number of solutions. The second case, one and only one solution, your trivial solution. And in the third case, absolutely no solutions will work. All right. So now we go to 4.1.2, which is the situation for homogeneous equations. Okay? And again, this is not the same as our homogeneous equations in first order differential equations. Okay? They use the same term, but it's different. And there is a little blurb I thought they had a little blurb here. Here it is. I think it's at the very end, the remarks. No, it's not there either. I think we'll hit it. I just can't remember where it is. Okay. Oh, here it is. Yeah. It's right here on page 121. And about the middle of that section, 4.1.2 on that page, it says the word homogeneous in this context does not refer to the coefficients that are homogeneous functions as in section 2.5. Okay? So those were homogeneous functions. These are homogeneous equations. Let's go back and make sure that that was the distinction made before. I'm pretty sure it was. 2.5. Whoops, right past that. Short section. No, they call them homogeneous equations too. But but then it said f is said to be a homogeneous function of degree alpha. And they just called the differential equation homogeneous. So it's a little sloppy, but it is indeed true. So it's a different meaning. This is for higher order homogeneous equations. Okay? We've seen this before. A sub n of x dn y dx n plus a sub n minus 1 of x dn minus 1 of y dx to the n minus 1 plus a sub n minus 2 as a function of x d to the n minus 2y dx to the n minus 2 n plus dot 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 all the way down to plus a sub 2 d2 y d2x dx squared plus a sub 1, that's a function of x dy dx plus a sub 0 of x y, which is a function of x, okay, plus, is equal to, this case, 0. Before we had a g of x there. If this is equal to 0 rather than some function of x, then this is what we mean by homogeneous equation. Now, I've mentioned it before too. If that's equal to 0, you have a homogeneous equation, differential equation. Now, that's opposed to, if this was equal to g of x, we call that a non-homogeneous. Okay, if you got a g of x there that's not. Okay. Now, here's a couple of examples. 2y double prime plus 3y prime minus 5y equals 0. Okay? Which is that? It's homogeneous, linear, second order differential equation. And guess what? You know that at least one trivial solution exists, y is equal to 0. Okay? That's always going to be true for homogeneous equations. Okay? You've got at least one, and that's the y equal to 0, the trivial solution. Whereas x cubed y triple prime plus 6y prime plus 10y is equal to e to the x, non-homogeneous. Okay. Now, doesn't matter what the derivatives are, doesn't matter what the coefficient functions are. If you have a 0 on the right-hand side, homogeneous, not a 0 on the right-hand side, non-homogeneous. Okay. Now, and that the second one there's a third order, but that doesn't really matter. Okay, we shall see that to solve a non-homogeneous linear equation like this one or that one, okay, we must first be able to solve the associated homogeneous equation. In this case, that would be this would equal to 0. In this case, rather e to the x, you would put a 0 in there. Solve that first, and then figure out what to do to make the other one work. Okay? And that's called the associated homogeneous equation. That's the thing with the 0 there. Okay? So, remember what the requirements are on some common interval I. Okay, we've hit these before. All your a sub x's here, every one of your a sub x's here, okay, Every one of those has to be continuous on that interval. And the g of x, if you have it, has to be continuous on the interval. And the one other thing is the a sub n of x cannot be 0 anywhere on that interval. Okay? We saw that in a previous example. Okay. Now, for some reason here, and there is a reason, they introduce these differential operators now. And if in higher level courses and stuff, you'll probably use these a lot more if you do that much more math. But I'm not absolutely certain that I see the advantage of doing it now, but I guess there may be a little bit. In calculus, differentiation is often denoted by the letter capital D. I think I'll go to a clean page here. Okay? I hope I won't regret it. Okay? So in other words, d by dx, that operator is now being defined as the capital letter D. Okay? The prime was done the same way, but now they're using that capital letter D. So if it's dy dx, that would be dy. That would be the first derivative of y. Okay? Just like here. Now, the symbol D, called that differential operator, because it transforms a differentiable function into another function. Okay? What do we mean by that? Okay? D of cosine 4x. What would that be? I'm sorry? Yeah, negative 4 sine 4x. You're absolutely right. That's it exactly. Okay? What would you mean by d of 5x cubed minus 6x squared? $15x squared, is that what you said? Minus 12x. Perfect. Okay? You got it down. Okay? Now, higher order derivatives can be expressed in terms of d as well. If you think that a higher order derivative like d by dx of dy dx, okay, we know that is d2y dx squared. That's what the second derivative is. But now think of it in terms of d's. That's d by dx of d by dx of y. Okay? Well, what is that? D by dx is d, so this is d squared y. So, again, y double prime says the same thing, okay? But there is a reason they like to do this, okay? So in general, and d n y dx to the n would be d to the nth of y, okay? That's your generalization there. Now, as long as y is differentiable, at all that many different derivatives, okay? Polynomial expressions involving d, such as d plus 3 or d squared plus 3d minus 4, okay, 5x cubed d cubed minus 6x squared d squared plus 4xd equal 9 are also differential operators. You just do. What it's saying is, you just assume that after these operators, you have some function, y or g or whatever, you know, and that would then be the first derivative of y plus 3y. That would be what the first one was. Second derivative of y plus 3 times the first derivative of y minus 4 times y. So you see that. And then you'd have 5x cubed times the third derivative of y with respect to x minus 6x squared times the second derivative of y with respect to x plus 4x times the first derivative of y with respect to x is equal to 9. That would, you just put the function at the end of that distributed. Okay. Now, getting stopped up again, this is driving me nuts. Okay. So in general, we define an nth order differential operator, or also called a polynomial operator, and here they introduce another letter, okay? And this is the letter L, okay, which means linear, and that would be a sub n of x dn plus a sub n minus 1 of x dn minus 1 plus a sub n minus 2 of x d to the n minus 2. See, it does cut down a lot of writing, okay? Plus dot, 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 plus down to a sub 2 of x d2 plus a sub 1 of x d plus a sub 0 of x is equal to g of x. Okay, now I'm having trouble remembering. Yeah, they just leave that a sub 0 of x. Understanding that all that's operating on some function y. But this is a linear operator, meaning you have a polynomial here, but it's a linear polynomial because none of these have crossed them, like a dn times a dn minus 2 or times a d squared or times a d or anything else. You don't have any of those, and none of these are squared themselves, like dn squared or anything else, or d squared out. Remember, this t squared this is the second derivative of d. Whereas dy dx squared, that's not the same as d squared. D squared is d2y dx squared. Remember, that's what your operator is. Okay. Now, so as a consequence of the two basic properties of differentiation, and basically I'm out of room, so I'm going to regret this, I'm sure, but I'm going to eliminate that. These are the two basic operators for linear functions that you have to have. And frankly, I think they put them in the wrong order. The first is the additive, which could be subtracted to property, which is that d onto two function f of x plus g of x is equal to df of x plus dg of x. That's always true. Okay? The second of these, which they list first, that d operating on a constant multiple times your f of x is the same as the constant multiple operating on d of f of x. Okay? That's the second linear operator, where c is any constant. Okay? So the differential operator L possesses a linearity property, that is, L operating on a linear combination of two differential functions that is the same as the linear combination of L operating on the individual functions, okay? Which here is sort of the thing that sort of combines these together, and this is usually a little easier to deal with. The L, get my symbols right, I think that's a brace, operating on, I think they use alpha of x plus beta g of x is going to be alpha L operating on alpha of x plus beta times L operating on g of x. I was lost where I was there for a minute. Okay. That sort of combines the additive feature with the constant multiple feature. Whereas the alpha and beta are multiple, the functions are being added together. This sort of combines both of those into one operation. Okay. And if that is met, it's a linear operator. Okay. For any constants alpha and beta that you have. Okay. Now, they introduce stuff and then sort of let it go. Okay. What was the point of that? Okay. Sure there is one. And you use those features in many other math courses as well. Okay. Linear algebra for one. Okay. Any linear differential operator can be expressed in terms of the D notation. So let's do it. So now it's sort of like we're going back to D's, but the L's are still going to be there. I think I'll start with a clean slate here. Y double prime plus 5y prime plus 6y is equal to 5x minus 3. Okay? That can be written in D terms, like you tell me. Yeah. Now D squared y, because it's the second derivative, right? So 5 dy, okay? The dy, yeah. Plus, huh? No, you don't need the d there because it's not a derivative, okay? That takes the place of it. Sorry. You do have the y there, but what they really meant for you to write it is this way. D2 plus 5d plus 6y. That's how they wanted you to do it, okay, is equal to 5x minus 3. Because all of it's operating on y. Even the 6 is operating on y because obviously it was up there too. But to write it in differential form, in D form, would be that, okay? And that would then be your linear operator, is that thing there. Now, you can write the linear nth order differential equations, 5 and 6 like we had before. No, I'm sorry. 6 and 7. Okay. If this then is your L, then you could say L of y is equal to, in this case, that would be your g of x. But if you're doing the homogeneous case, that would be L of y is equal to 0. Okay. Now, dropping that and going to something else. Superposition principle. The next theorem, we see that the sum or superposition of two or more solutions of a homogeneous linear differential equation is also a solution. Okay? So let's start with a clean one here. Let's say that y1, y2, y3, dot, 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 all the way up to y sub k, I think is what they use here, that all of those, each of those are solutions of the homogeneous nth order differential equation. Okay? On the interval I. Okay. These are all solutions. If they are all solutions, then here is what we call the general solution. Y is equal to C1 y1 of x plus C2 y2 of x plus C3 y3 of x plus dot 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 plus as many as you need here, C sub k y sub k of x. Okay? What that means, if you know these individually are solutions for your differential equation, then any linear combination of them, which means any constant, your choice of constant, times the first one plus some other constant times the second one. The subscripts here are just saying this is the one that goes with that and this is the one that goes with that. These are just any old constants that you put there. Those will also be solutions, okay, for any Ci where I goes from 1 to k. And they're arbitrary constants, anything. They're also solutions on the interval, okay? Now there's a corollary to that one. Sorry. A constant multiple, y is equal to C1 y1 of x, okay, of a solution of y of x, y1 of x, okay, of a homogeneous linear is also a solution. So basically, if you just know one solution, any constant times that solution is also a solution, okay? The B part of that is a homogeneous linear differential equation always possesses, if it's homogeneous, if it's equal to 0, then y equals 0 is a solution. One of those many solutions is a solution, okay? It's called the trivial solution. All right, let's go to example 4. Okay.
So this denotation is going to be used like for the rest of
That's the problem. There will be some places they use it, and sometimes you'll go for pages without using it. But they're just sort of introducing it. As it said, this is preliminary theory. I think a better word would be preliminary nomenclature. You know, just to get it all out there in front of you, that you've seen it before, and then they'll just pick it up whenever they choose to. Oh, as you remember from this, so it's just, I don't know if this is a good illustration or not. I've often heard this called the shotgun approach. Throw everything out there, and then if you ever need anything, pick it up. Okay. This is a really dumb example of this, but I took an upper level physics course from this really brilliant British physicist, theoretician. He was all into theory. Don't know if he could apply a thing, but he was into the theory. And he was up there proving things. He hardly ever wrote a number on the board. It was all letters, okay? Always letters, okay? Subscripted letters, non-subscripted, stuff like this. We had a kid in our class who was he was just a classic nerd, okay? Brilliant guy, okay? Obviously a brilliant guy. He stayed on top of everything. The rest of us were floundering around trying to make sense of it. He was on top of it as soon as it was out of the professor's mouth almost. So he always sat right in the front of the class, big guy, sort of good, not huge, but good-sized guy. His glasses had a slant to them, made him look even nerdier and stuff. But he sat right in front, and he'd be following along, writing down, and all of a sudden the hand would go up. I mean, it would just shoot up into the air, and just demanding the professor say, "Yes, what is it, Mr. Thomas? Shouldn't that be a minus sign? Shouldn't this be a 3 there?" Yeah, he just caught everything, it seemed like. Well, Dr. Gatlin was up there doing his thing, and he couldn't care less about minus signs or other things like this. So after about the second or third interruption of the morning, he was just writing away like crazy. He had a bunch of panels of boards. They were all chalkboards back then. So he went down to the last panel and took his chalk and marked off a corner. He put plus, minus, plus, minus, minus, plus, plus, plus. He said, there they are, put them where they need to go. So it's sort of like what they're doing here. They're giving you all this stuff, and then when they need it, they say, give that, and put it where it needs to go, okay? So they're just introducing it to you. Not really doing a lot with it yet, but introducing it. So let's try example 4. Here are some functions. y1 is equal to x squared. Good little function. y2 is equal to x squared log x. Okay? Their contention is both of these are solutions for the homogeneous linear equation x cubed y triple prime. Have we seen this before? Seems like I just have written this down. So, I don't see it now. It seems like I've written this recently. And this book does tend to pick up and use the things again. Maybe not. I recognize the first part, but not the back. Minus 2x y prime plus 4y is equal to 0. Okay? On the interval 0 to infinity. Okay? Now, they claim that both of these functions are solutions to that. Being a cynic that I am, let's just verify it. Okay? What's y1 prime? What would that be? Yeah. 2x. And y1 double prime, 2. And y1 triple prime, 0. Okay? Let's plug that in and see if it works. That would be 0 minus 2x. That would be 4x squared plus 4 times x squared. Sure enough, that's equal to 0. Got it. So that one worked. The other one's not going to be nearly as nice. I'm going to erase those now. This is just verifying because I'm a cynic. Okay? So be a little bit more involved on this one. So let's do the y2 here. Okay? y2 prime would be 2x log x, because you do first, the derivative first times the second, plus x squared over x, right? Okay, so that would be just x. Okay, y2 double prime would be 2x over x. Okay, that'll be 2 plus 2 log x plus 1, right? Because you have the x there. Yeah. Okay. One more. y2 triple prime is going to be 2 over x, right? That's all, folks. Okay? So let's see what we got now. X cubed times 2 over x be 2x squared, right? Minus 2x times y prime would be 2x log x plus x plus 4y, which is x squared log x, and supposedly that's equal to 0. Man, my eyes are itchy. See what we got. This is 2x squared minus 4x squared log x minus 2x squared plus 4x squared log x. 2x squared minus 2x squared minus 4, sure enough, equal to 0. So, both of those satisfy that linear, ordinary, third degree differential equation. Okay? Now, by the superposition principle, your y is equal to c1 x squared plus c2 x squared log x. Okay? Also is a solution for that differential equation. Okay? That's all they're doing, okay? Just saying that then is also a solution. Here's another situation with it. They're saying y is equal to e to the 7th x. They say that's the solution of this differential equation. Y double prime minus 9y prime plus 14y equals 0. Okay. Yeah. So stiff. Let's go on and do our derivatives. Y prime would be equal to 7e to the 7x. And y double prime would be 49e to the 7x. So plug in here, 49e to the 7x minus 9 times 7 is 63e to the 7x plus 14 e to the 7x. Is that equal to 0? Let's add the positives together. You get 14 and 49 would be 63 e to the 7x minus 63. So, yep, sure would. Well, since that's a solution, then y is equal to C1 e to the 7x would also be a solution. Okay? Or you don't need the 1 there, since it's the only constant. Since it's the only constant you have, it would be c e to the 7x, also a solution. For various values of c, we see that y is equal to 9e to the 7x, 0, that's the value for c, negative root 5e to the 7x, they're all solutions to the equation. Infinite number of them. All right, now, another concept they're going to throw forward here, and again, something you probably use in other classes even more than this one, but it is true in this too. And that's the concept of linear dependence versus linear independence. So the next two concepts are basic to the study of linear differential equations. Okay? Definition 4.1.1. Either linear dependence or independence. A set of functions, f1 of x, f2 of x, f3 of x, up to fn of x, is said to be linearly dependent. I'm going to clear. I was thinking I could get it, but I'm afraid not, so let me just clear. So here we have a set of functions. f1 of x, f2 of x, f3 of x, all the way up to and including, they're using n this time, f sub n of x. Okay, n different functions of x. They are linearly dependent if, on an interval I, if there exist constants man, eyes have just gotten so dry. If there exist constants, C1, C2, C3, all the way up to and including Cn, one for each one, and these constants are not all 0. Now, if all those constants were 0 and you multiply them by the functions, everything's going to be 0. So we've got to require that not all the constants are 0. Okay? Now, if then you did C1 F1 of x plus C2 F2 of x plus C3 F3 of x plus ... all the way up to and including Cn Fn of x. If there's some combination of these where the c's are not all 0 that when you add them together, you get 0. Okay? What that means is at least one of those can be written in the terms of all the others. If that's true, and not all the C's are 0, then pick one, any one of them. One of these in here. See some I, where I is somewhere between 1 and n. And write it by itself and subtract all the others to the other side. Or take this one and subtract it to the other side, leave all these others in here, that would be less writing. Then that says that this function can be built from some combination of all the other functions. That means they're linearly dependent on each other. Okay. Now, and that's for every x in the interval. Okay. If the set of functions is not linearly dependent, in other words, there's not a set of c's, not all 0, that makes that true, then they're linearly independent. In other words, the only way you can get that equals to 0 is if every c was a 0. In other words, you can't isolate one and say it can be written in terms of the others. If that's the case, they're linearly independent. Okay? In other words, a set of functions is linearly independent on some interval I if the only constants for which that combination is equal to 0 is true. It's saying the same thing I did. All the c's would have to be 0. If that's the case, they're linearly independent. It says here it's easy to understand these definitions for a set consisting of two functions, f1 and f2. If the set of the two functions is linearly dependent on an interval, then there exists some constant c1 and c2, not both 0, such that for every x in the interval, c1 f1 plus c2 f2 is equal to 0. Okay? Therefore, we assume that c1 is not equal to 0. It follows that the function that f1 is equal to some combination minus c2 over c1 f2. That is, if a set of two functions is linearly dependent, one function is simply a constant multiple of the other. Now, when you get 3 or more functions, you can't say that. Certainly it would be true if that were true, but they can get a lot more complex after that. But with just 2, one of them is a multiple of the other. Okay. We conclude that a set of two functions f1 and f2 are linearly independent when neither function is a constant multiple of the other on the interval. Okay? If f1 happens to be sine of 3x, for example, the set of functions f1 is sine of 2x, f2 is sine x cosine x. They're linearly dependent. So, yeah, I think I can get it here. If f1 of x was sine of 2x, and f2 of x is sine x cosine x. Okay, interesting they chose those two. Do you happen to remember your double angle formula? Okay. What's that? No, okay. Yeah, you're thinking of going the other way. let's go up and do sine of, I'm just going to call it alpha plus beta. Okay. Do you remember what that is? That's sine alpha cosine beta plus cosine alpha sine beta. Okay. That's the sum angle formula. Okay. Now, what if alpha and beta are equal to each other? Well, then this becomes sine of 2 alpha, and that would be sine alpha cosine, I said alpha and wrote beta, goodness gracious. Goodness, I'm getting so hungry. Sine alpha cosine alpha, because alpha is equal to beta, okay, plus cosine alpha sine alpha. Well, guess what? That's 2 sine alpha cosine alpha. Well, guess what? These two functions, sine 2 alpha and sine alpha, or sine 2x and sine x cosine x, guess what? Just multiply the second one by 2, and you've got the first one. Okay? So yeah, they're multiples of each other. So therefore, they're linearly dependent. That's exactly what I said. Okay. On the other hand, a set of functions f of x, and here they have a picture of this one. So I think I'm going to clear the screen for it. Man. No, I saw it. There it is. So f1 of x is equal to x. f2 of x is equal to absolute value of x. Okay? That set is linearly independent. Even though, and this is for all x's is true, even though f of x equal x is the identity function, and f of x is absolute value x, half of that is the identity function, but then the other half is the negative of it. That's not a multiple of each other. It can't be, okay? Even though this leg are identical, this leg over here cannot come from that leg, okay? Even if you did minus of that, but then you would have something else. So yeah, they are not multiples of each other, so they're linearly independent of each other, okay? On the interval from minus infinity to infinity. However, if you limit it to interval to be 0 to infinity, they'd be identical, because the absolute value of x is x in that interval. But if you did on the whole interval, minus infinity to infinity, they would be identical. They would be independent, linearly independent. Now, so another thing you can do is do f2 of x. If you only have two functions divided by f1 of x, if this comes up to be some constant c, then you have dependent, and if you cannot equal some constant c, they're independent, okay? So let's do example 5. Here's a set of functions. f1 of x is equal to cosine squared x. f2 of x is equal to sine squared x. f3 of x is equal to secant squared x. and F4 of x is equal to tangent squared x. All right. They claim that this set is linearly dependent on the interval minus pi halves to pi halves. Now, why didn't they go negative infinity to infinity? That's what? I can't hear you. Okay. Here's the main reason. Think of tangent x, just tangent x. It's only defined from minus pi halves to pi halves continuously. Then you have a vertical asymptote. Guess what? You can't have discontinuous functions on that. So, yeah, you have to have limit there. Secant has the same limitation. It's not defined at minus pi halves to pi halves. Sines and cosines could be anywhere, but not secant and cos. Secant and tangent, they are limited there, so you have to do that. Now, what makes them linearly dependent? Well, it says that some linear combination can't be zero, okay? And I'm just going to get one example, okay? And I hope you recognize this. What is F1 plus F2? Huh? No. Easier. Yes, it's 1. Okay, that's 1. Now, I don't know, do you remember a relationship between sine squared and secant squared? How does that go? I mean, tangent squared and secant squared? Tangent squared x plus 1 equal secant squared x. Okay. How do you get that? Divide your earlier one, sine squared plus cosine squared equal 1. Divide everything by cosine squared. And that would be sine squared over cosine squared, tangent. Cosine squared over sine squared, cosine squared is 1. And 1 over cosine squared is secant squared, right? So that's true. Well, guess what? Then you could say that secant squared x minus tangent squared x, guess what that's equal to? One. Okay? Well, guess what? This would be F3 minus F4 would equal 1. Well, what if you said F1 plus F2 minus F3 plus F4? What would that equal to? 1 minus 1, 0. Okay, there you have a linear equation in those 4 functions, and not all the coefficients. In fact, none of the coefficients are 0, and you still have 0. That's linear dependence. Okay? Now, that's just one way. Maybe other ways, maybe easier ways, but that's one. Where in the world was that? Okay, there it is. No. Oh, that was it. Example 5, bottom of the page. Okay? Now, they just said, they said C1 and C2 equal 1, C3 equal minus 1, C4 equal 1. Yep. Sure enough, that adds to 0. Okay, now here is something saying the same thing, and I've already mentioned this. If indeed you can have a linear combination of all those functions equal to 0, okay, with not all the coefficients equal to 0, that means you can take any one of those functions that's in there with a non-zero coefficient, solve for that, and you get some linear combination of all the others. Okay? And that's what they're saying here. So let me erase all the ink. And they're saying a set of n functions, f1 of x, f2 of x, f3 of x, dot, 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 up to and including fn of x. Okay? These are linearly dependent, or if they are linearly dependent, on some interval I, okay, if at least one of the functions can be expressed as a linear combination of the remaining functions. If one of these, say f sub I of x, is equal to the sum of all, some linear combination of the rest of them, okay? So that would be C1 F1 of x plus C2 F2 of x plus C3 F3 of x plus dot, 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 up to plus F I minus 1 of x plus, oh wait, C I minus 1, okay, plus C I plus 1 F of I plus 1 of x plus dot, dot, dot on up to C n F n of x. Okay. And then that's saying basically you just subtract all the others and isolate the one that wasn't a zero, and you've got it. Okay. They show a much smaller case. If you just had three functions, f1, f2, and f3, and they're linearly dependent, then solve for f3, and you have some linear combination of f1 and 2. Okay, and that'll be true for all x's in I. Okay, set of functions is linearly independent if there's no one function can be a linear combination of any of the others. So let's do, oh wait, finally feeling a little better, and we ran out of time. Though I definitely feel like I could eat something, so I think I'll go do that. We're going to start next time with example 6, and in this section you can do homework exercises 1 or 3 or both, 5 or 7 or both, do 9, you can do 11 if you want to. That has hyperbolic sines and cosines. I really don't care for them that much, but if you look them up and use them, you see it works. I think you can do 13. Any of the odds 15 to 21. Let's see how far we got here. And try to do some of 23. I'd say stop at 21. We'll do some of the rest of those and pick up from there. Okay. All right. Now let's remind myself. Today we started with 2.8, was it? Is that what it was? 2.6. And then we did 4.1. All right. Good deal.